In this, we are going to cover another micro machining process, namely focused ion beam machining. As the name suggests, it uses a beam of ions focused at a particular point on workpiece from which material is to be removed. This ion beam forces out the material from the workpiece. This process is also known as ion milling. And why ions? Because they are nothing but atoms having gained or lost an electron, which are much heavier than your normal electrons. For example, an hydrogen ion is 1840 times heavier than the electron. So this process offers certain advantages over electron beam machining. This is non-contact process, so workpiece is completely stress-free and obviously works better on nano or micro scale, so used for micro machining. It is also coupled with scanning electron microscope, that is SEM, which is basically a microscopy which is used for imaging the whatever process is going on. So imaging gives you better control over milling and machining process. So yes, focused ion beam machining is used usually in collaboration with scanning electron microscope. Now let's see the basic of focused ion beam machining. This is ion beam generated from the ion column, which is most of the times gallium plus ions. That is a workpiece. These are the these represents the atoms which are removed from the workpiece. So, how does this work? There are certain steps involved. The first and foremost of them is surely sputtering. Sputtering can be thought of as a game of pool or a game of marbles. Mm. What happens when an ion accelerated with a high velocity hits the work surface? It transfers this kinetic energy to the surface atoms of that workpiece, and if that kinetic energy is happen to be greater than the binding energy of that particular atom which it is hitting on the surface of workpiece, then the kinetic energy counteracts the binding energy and that atom is forced out or emitted out from the workpiece. This is nothing but a sputtering. So sputtering contributes to machining you in ion beam machining. There is a parameter for this called sputtering yield, which is basically a ratio of mean numbers of emitted electron atoms to the incident particles which ion beam contains. That gives us how much incident atom can generate how many emitting atoms from the workpiece. Sputtering also gives rise to collision cascade. If an ion incident on the workpiece possesses a higher energy, then it does not only transfer that to single atom on the surface, it undergoes series of collision inside the target. And each atom which comes in contact with this acquires kinetic energy. If as good as in sputtering, this kinetic energy is more than its binding energy, this atom can be emitted out from the workpiece. So collision cascade can emit several atoms at a particular time from the target surface. And also the incident ion can get implanted in the surface so that it can damage the crystal lattice of the target surface. The cascading effect can be accelerated by using higher energy incident ion. Cascading effect is accelerated when higher material removal rate is needed from ion milling, and though it causes some surface damages, it still yields higher sputter yield. As we surely know, one problem gives rise to another. If collision cascade occurs, the ions can get implanted deep in the surface of workpiece to be machined. This can cause point defects in the crystalline structure of the workpiece, and that causes the crystalline structure of the workpiece to convert into amorphous structure, which can be harmful at the times. The depth of this is very small, 10 to 30 nanometers, but as this is a micro machining process, it affects. Mm. There is another phenomenon observed in the ion beam machining process, that is of redeposition. As this whole process is occurring in the vacuum, what happens is the atoms removed by the sputtering process can not be evacuated by the vacuum system. Sometimes they can get deposited to the adjacent surface where the milling is going on. The redeposition material sometimes settle on the site and adhere to the surface. That is, we need to sputter it second time, which obviously increases your process time and efforts. So redeposition is surely undesirable phenomenon in the focused ion beam machining. Redeposition is observed highly when are holes or trenches or narrow slots where the redeposition is also difficult to be evacuated. Up to now, we have seen sputtering, collision cascade, amorphization, and redeposition. Although there are arguments, but redeposition is surely unwanted phenomenon in focused ion beam machining. So we need to get rid of it. That can be achieved using two methods. The first is low beam current with multiple passes. If the incident ion beam does not have eye energy, the collision cascade is minimized and therefore the dislocation of the atoms inside the crystalline surface of the workpiece is minimum. But as the material removal rate in this process is going to be very low, we need multiple passes. So lower the beam current, use the more passes. That is one of the things which we can use to avoid the dedeposition. The second thing which can be done is parallel milling. Parallel milling is machining multiple patterns at the same time. For example, drilling one hole after another is series milling, and drilling 15 or 10 hole on the particular surface at the same time is called as parallel milling. Parallel milling avoids redeposition as all the patterns are machined at the same time. To overcome both redeposition and low material removal rate problem of the focused ion beam machining, reactive gas can be introduced at the site of milling. This type of milling is called as gas assisted focused ion beam machining. So this is GIS, that is gas injection system, in addition to ion beams and workpiece. So this reactive gas is incident on the milling site. Gas molecules get adsorbed, that is they rest on the surface of the workpiece. When ion impinges on the surface, the adsorbed gas atoms ionize and they chemically react with the substrate surface, which helps the milling process. This compound does form can most of the times be volatile, so it is removed out from the workpiece. So reactive gas deposits on the surface, reacts with the ion and obviously workpiece and removed as a volatile material. This will obviously solve the problem of redeposition, thereby increasing the accuracy of the machined feature and enhances the material removal rate. So, for the number of gas molecules or the amount of gas injected at the milling surface is kept to be optimum, because if the gas is lower, that is in less amount, it will generate less sputtering yield, that is low material removal rate. But if there is an excess gas, the gas atom will directly interact with the ions and not the workpiece, that is the substrate. So there will be no workpiece or workpiece atom removal, and again low sputtering yield. So either high or less amount of gas results in low material removal rate. Selection of suitable gas is done based on whatever the workpiece or the target material we are using in this process. Generally, the halogen based compounds are used as a reactive gases such as iodine, bromine, or xenon difluoride. These are some examples of commonly used gases. Let's move on to the instrumentation of focused ion beam machining. Commercial dual beam platform incorporate both focused ion beam column and scanning electron microscope column, in which ion beam column is used to generate ion beam which is used for machining the substrate or workpiece, and electron column generates beam of electron which can be scanned over to the workpiece to get in situ real time image for observing the FIB process at the target zone. Typically, the ion column is tilted at 52 degree to the electron column so that the real-time image can be seen on the computer screen. In case of gas-assisted FIB machining, there is another nozzle in the setup which is from the GIS, that is gas injected system. So the instrumentation also includes goniometer sample stage, that is the stage at which the substrate or workpiece is held, and pumping system for creating vacuum condition, which is favorable for both electron beam and ion beam. So there are total five aspects: ion column, electron column, gas injection system, goniometer sample stage, and pumping system. Let us discuss the ion column in detail. This is general schematic of ion column. Firstly, it has ion source for generating the ions. It can be of two types: liquid metal ion source LMIS or gas filled ion source. Most of the FIB uses LMIS, which is common and has gallium Ga plus ions as it has low melting point. Gas filled ion source can generally be hydrogen or helium gases. From liquid metal ion source, the ions are field evaporated and forced to travel downwards. Next important part is mass selector. It is a setup that allows only required number of ions with fixed mass charge ratio to pass through it for the machining process. Then there is an aperture or a drift tube which allows only the atoms which are traveling in a vertical direction. Then there is a set of lenses out of which the condenser lens controls the diameter of ion beam. That is, it can increase and decrease the size or the circumference of the ion beam. And objective lens are useful for focusing ion beam at the single point at the sample. Sputtering occurs when these ion beams strike the sample surface. Electron column is similar to ion column, or it is also called as SEM column. The source of electron beam is kept at the top of the column which emits electron, and they are accelerated towards the sample. The electromagnetic lens are used to focus this beam of electron on the sample. When beam of electron strikes the sample, the surface emits secondary electron, and this secondary electron can be detected using detectors which are capable of converting this electronic signal into an image. Electron column is in detail discussed at the video of scanning electron microscope or electron microscope. So please refer to that. Gas injection system allows introducing small quantities of the reactive gas near the target surface. For controlling the flow of gas, it usually has a tungsten needle with a reservoir containing precursor material. The goniometer sample stage, that is the stage at which the workpiece is held, can provide three-dimensional motion x, y, and z axis, and it can rotate around its own axis. Also, it can tilt the sample in 60 degree if required. This is a standard stage which is used in many machining processes. It can handle the size approximately up to the 10 centimeter depending upon the chamber size. The position of the sample stage is controlled by optical encoder with high precision. The pumping system mostly contains a vacuum pump which is used to create and maintain ultra high vacuum condition, which is both required for the ion column and electron column to work properly. Now, to govern the process of machining, we must learn about the factors which affect the machining characteristics of focused ion beam milling process. Following equation gives the material removal rate in terms of different parameters, in which Y is a sputter yield, I is a probe current, A is the area that is to be etched, rho is the density of the target material or the workpiece, M is atomic mass of the target material, and E is the charge emitted. So all these parameters contribute to the final quality of the machining. This can be summarized as four input parameters. First is workpiece material. As material removal rate depends upon density and atomic mass, the nature of workpiece material affects the machining characteristics greatly. Second is angle of incident. Because sputtering yield depends upon ion incident angle. Increasing this angle increases the number of incident of ion atom interaction, which results in increase in sputtering yield. But it cannot be kept as 90 degrees because there is a higher probability of collision between the incident ions and the sputtered out ion to interact with each other. So the ion may not reach the work surface when it is kept to be 90-degree. Therefore, the range is kept to be 75-degree to 80-degree at which we can get the maximum sputtering yield. Next is ion energy. The sputtering process occurs when the transfer of kinetic energy is from ions incident to the workpiece atoms. So, this energy must be kept above the binding energy of the atoms of the workpiece materials. Current density. The rate of material removal is directly proportional to probe current. So, higher is the current density, higher is the material removal rate. Focused ion beam has vast set of applications in both imaging and machining as well as in deposition. But strictly speaking about machining, it can be used for micro and nano machining due to its low material removal rate. It is also used for preparing samples for TEM, transmission electron microscopy, because it can produce ultra thin and uniform lamellae, almost electron transparent for observation under TEM. It is also used for manufacturing the atomic force microscope tip, which is again has very small dimension, and it is used for controlling size and shape of nanostructures in microcomponents. Another application involves lithography, which is another nanofabrication process which is used for creating patterns on the substrate surface. So that's it, folks. Thank you for being here and hope you enjoyed this.